All right, I wanted to answer a few of the questions that were sent to me through email about the homework for exam three. First one was 1G, uh, DTC, that has this formula. Your S and your carbon and your S here, this is an eta 3. All right, so you count an eta 3 as a 4 minus 1. There are two of those. So over here, I have the total. Both of my eta 3s are both 4 electron minus 1s. So that's this one and this one. Then you have your alkene, that's a 2-0. Then you have your alkyne, which could be a 2-0 or a 4-0. So I'm going to get the tungsten. So this is minus 1, this is minus 1. Overall, we're neutral. So tungsten has to be tungsten 2, which is D4. All right, and so then you add up what you have so far. You got your 4, your 4, your 2, and your 4. So your total is 14. And so to get 18, we have our alkyne that is going to be getting 2 electrons from the PY-PY overlap and the PZ-PZ overlap to give you an 18 electron complex. So your triple bonds, they can either give you 2-0 or 4-0. Whichever one gives you the 18 electrons, that is the one that we will use. Second question was on 2G. All right, so you've got RO, you've got 3 of them. If you draw the Lewis structure of RO, you see that that is the same as an OH Lewis structure. All right, so you got a 2 electron minus 1. You got 3 of them, so that's 6 electrons minus 3. Then you've got an alkyne that is attached as a triple bond. So when you draw the Lewis structure, if we look at the Lewis structure of a carbon with a CH3, and it has 3 electron pairs. So carbon is supposed to have 4 electrons, this one has 7, and that's how you get the minus 3. And it is donating 2, 4, and 6 electrons. So that is a 6 electron minus 3. All right, and so now you've got your 6 electron minus 3 from your 3 ROs, and you've got your 6 electron minus 3 from your alkyne. So you've got 12 electrons, and so your tungsten has to be the plus 6 in order to neutralize the minus 6, so that's D0. All right, so here you'd have a 12 electron complex. You would not predict that to be stable. The one before that, if it was a prediction question, number 1 was not, but it's 18, so you would predict it to be stable. 2I was the next one. All right, so again, it is about this triple bond and how you count it. So anytime you have a triple bond metal to carbon, it will always be counted as a 6 electron minus 3. Bromine is a 2 electron minus 1. 4 COs, 8 electron 0. All right, and so our oxidation of our tungsten, you have your minus 3, your minus 1. Overall is neutral, so it's a tungsten 4, D2. And so when you add up your 8 and your 2 for 10, 2 is 12, 6, 18 electrons total. And so, yes, you would predict that to be a stable complex. 2N, CP, if it says CP, it is a 6 electron minus 1. All right, so you got your 6 electron minus 1 for your CP. NO, this one is difficult because it can be a 2 plus 1 and since there's 2 of them, one could be plus, one could be minus, both of them plus, both of them minus. You're going to give the one that gives you an 18 electron complex. That's why it's an and or. All right, and then hydride is 2 minus 1. So I usually go with the 2 plus first and see how that works out. All right, so I have my 6 minus 1. If I have 2 of them that are 2 plus, that gives me a 4 and a plus 2. And then my hydride is a 2 minus 1. And so I have a minus 1, a plus 2, and a minus 1. It is neutral. Tungsten 0, D6. 6 and 4, 14, and 6, 16, and 2, 18. So picking the 2 and the plus 1 was the correct answer. That's 18 electrons. And that means that the structure of your NO is linear. If we went with the 4 minus 2, over here I go with the electron count. So you still have your 6 minus 1 and your 2 minus 1. And now you have a 4 minus 2 if it were bent. But now we have minus 4. So now it's tungsten 4, which is D2. And so you add up your 6, your 4, your 2, and your 2. And that only gives you 14 electrons. All right. And if one was the 2 plus and one was the 2 minus, it would have been 16 electrons. You always predict the one that is 18 electrons. All right. So you draw the Lewis structure of the triple bond in there. So you're going to donate the 2 electrons, and it's going to have a plus charge. Now, if it's bent, here's the bent structure. So now you have 4 electrons on this nitrogen. That's a minus 1, and it's still donating 2 electrons. All right, and then 2O, so you would predict that to be stable. It's 18 electrons. You would predict anything 16 or 18 to be stable. So again, we have NO, and again, it's either going to be 2 plus or it's going to be 2 minus. So I will pick 2 plus first and see how that works. My CO is 2,0. My phosphine is 4,0. There's 2 of them, so it's 4,0. Cl is 2 minus 1. NO, I'm going with 2 plus first. All right, so when I go with 2 plus, that means this is minus 1, that's plus 1. It's neutral, but the overall charge is plus. So I have iridium 1, which is D8, plus 2 from the CO, 4 from the 2 phosphines, 2 from the Cl, and 2 from the NO, and that is 18 electrons. If you went with the 2 minus 1, now you've got iridium 3, which is D6, and then you add them up and you only have 16 electrons. So this one, again, is a linear NO. A 2 plus 1 gives you an 18 electron complex. The next question was 2Q. So I wrote out the structure. All right, and so when this is attached, this carbon and this carbon, I like to write the electrons so I can do the formal charge. So your carbon is supposed to have 4 bonds, no electron pairs. When it has an electron pair and 3 bonds, it has a minus 1 charge. So both of these are 2 minus 1. Phosphines are 2, 0, and your halide is 2 minus 1. All right, and so you've got your minus 1, your minus 1, your minus 1. So you have rhodium 3, which is D6, and then you got your 4, and your 2. So this one has a total of 16 electrons, and so you would predict that to be stable. 16 and 18 are the 2 most common stable number of electrons. 2s is the next one. All right, and so we have our diphos, which they give you the structure of on part R. It tells you that your diphos, the P's are diphos, and in number 1, you have the structure of that. So I wrote that structure just like you saw in question 1. And so you're getting a 2 electron 0 here, so a phosphine, and a 2 electron 0 here, CO, 2 electron 0. This is an eta 3, and so this is a 4 electron minus 1. Now, how do we count this? So over here, I have it written out. Again, when you have a bond, that comes from the 2 electrons, a coordinate covalent bond. All right, and so here we have our carbon, just like we had in the previous problem, as a 2 electron minus 1. Now this carbon has 1, 2, 3, 4, 5, 6 electrons around it, and so it has a minus 2 charge, and it's donating 4 electrons. So that is a 4 and a minus 2. And since this does not have resonance, this is just a methyl or an ethyl or whatever R group you want to pick there, then we have a Schrock carbene. So a Schrock carbene is a 4 electron minus 2. All right, and when you add all of the ligand electrons up, your diphos, you've got your 4, 0, you got your eta 3, 4, 0, you got your CO, 2, 0, and then you have your 6 minus 3. And so that is going to add up to 16. You got your minus 1, your minus 3, a total of minus 4. And so your tungsten has to be a plus 4 tungsten, which is D2. And your 16 and your 2 will give you an 18 electron complex. So this is your ligand electrons. So you always take your ligand electrons, add your d electrons, and that is 18 electrons. And yes, you would predict that to be stable. All right, the next question was 3D, where we have multiple metals. So we have a bridging halide. And so when you have a bridging halide, that means that you have 2 electrons going to one metal and 2 electrons going to the other metal. And so that's donating 2 electrons to each metal, so a total of 4 electrons, and your halides have a -1 charge. When you're bridging a CH2, all right, so you have this structure. So this has 6 electrons. That's -2 as the formal charge. And you got 2 electrons going to that metal and 2 electrons going to the other metal. And so it is a 4 electron -2. All right. And so, of course, your COs are all 2 0. Since we have 10 of them, it is 20 and 0. The overall charge is a -1. And so your osmium has to be a 2. So it is osmium, all 3 of them has to be a +2. And so I broke it into an osmium 1, an osmium 1, an osmium 0. So it's D7, D7, and D8. If you had a 2, a 0, and a 0, you would still get the same total number of D electrons. All right, so you've got your 22 D electrons plus your 4, 26, plus your 4, 30, plus your 20 from your 10 COs, 50. So you have a total of 50 electrons. And when you come over here and you multiply 18 by 3, we want to have 18 electrons at each metal center. That would be 54 electrons. All right, and so we do our 54 minus the 50 divided by 2, and so we have 2 metal-metal bonds. All right, and so the only way we can do it is to put osmium and osmium as the 2 metal-metal bonds. But these are bridging, and so you're going to bridge the other, so the osmium that does not have a bond to them, it is going to bridge. You're going to bridge your halogen and you're going to bridge your CH2. And then you put 3 CO ligands here, 3 CO ligands there, 4 CO ligands there, and you have an overall charge of a -1. And each one of those has an 18 electron osmium center. Right. And that was the end of the questions.